So here we go, chapter 5 about electron structure. So far at GCSE, we introduced this idea that the electrons existed at discrete energy levels, almost like the orbits of planets around the Sun, with 2 in the innermost shell, and then 8 in the next shell, and then 8, and then 18, 18, 32 onwards. Now this is evident in the shape and dimensions of the periodic table. For if you look in each period, how many groups are present? That is how many electrons there are in that shell. So you can see that for the first period with hydrogen and helium, there are only 2 elements there, indicating that there are only 2 spaces in the innermost shell. And then, of course, there are 8 across period 2, and on and on. And what you can see when you lay out the periodic table, so that you've actually put the lanthanides and the actinides in between the transition metals and group 1 and 2, what you can see is that this really does map out the electron configuration as we've understood it so far. But this is not the end of the story. We're going to advance this idea, but we're not going to throw it out entirely. This is a very powerful idea, and it does explain certain things. The model is similar to the solar system model, where you have planets orbiting at certain positions that correspond to the energy that they have. As they get further away from the Sun, they get more and more gravitational potential energy. Here, it would be electrostatic energy. You'd get more the further out you were. But of course, the interaction of the planets with each other prevent planets from forming in between. The orbits are here or there. There are allowed states where planets can form. Now it's the same with the electron. The interaction between them means that they can exist in some places, but not others. They can have some energies, but not other energies. Now if we were to count these places where they appear, we would call them the shells or energy levels. And we denote which shell an electron is in with a quantum number that we call the principal quantum number. We say for the 2 electrons that are closest to the nucleus, they are in the n equals 1 quantum number, and then n equals 2, n equals 3. Now these don't entirely map to the periodic table. It might be nice to think that period 1 is that n equals 1, period 2 is that n equals 2. There is a problem, and we'll introduce that later on. But for now, you need to imagine that it is like planets in some way, but different in other ways. With the solar system, the positions of the planets are really well defined. When you observe where they are and their motion, you know where they're going to be at any point in the future. If you turn around and look back, the moon will be exactly where you expected it to be. Electrons don't behave in this manner. They're not nearly so predictable. In the 1920s, pioneered by scientists like Max Planck, Wolfgang Pauli, Werner Heisenberg, and Erwin Schrödinger, we had the formulation of quantum mechanics. The basic idea is this: if I fire an electron at 2 little gaps in a screen, and then looked at the pattern on a screen behind that, I find something different depending on what I do as an observer. If I look at the electrons going through those 2 little gaps, I find that on the far wall a pattern of splatter marks that look like a sort of silhouette of the 2 gaps, akin to firing a paintball gun at a doorway. I expect to see paint in the shape of a doorway on the other side. That's what they did whilst they were observed. But when they were not observed, we saw on that far screen an interference pattern, which is wave behavior. The behavior where one wave actually superimposes on another wave. You have peaks and troughs cancelling out, and peaks forming constructive superpositions. It was behaving like a wave when it wasn't being observed. Now, a lot of the time, the electrons going around the nucleus of the atom are not observed. They do not give away their position until, for example, a photon of light strikes them. It means that most of the time the electrons are behaving as waves, and that wave distributes itself around the atom. It doesn't exist in any one place. It kind of exists everywhere that it can exist simultaneously. Now this, the wave-particle duality of the electron, means that the electron is not like a planet. It's not like a hard little nugget exactly where you expect it to be. Its position in space is defined by a diffuse area where we might find it if we looked. And these we call orbitals. Now we can find the shape of these orbitals using the Schrödinger equation, which is a very, very complex way of describing the wave behavior of something like an electron. But it wasn't this way that we first found out about the orbitals around the electrons. It was through direct observation. Before we get to those observations, let's look a little bit about what we think was being observed. There are regions in space around the nucleus where there's a high probability of finding the electron. What was realized by Wolfgang Pauli, something called the Pauli exclusion principle, which is that you can't get two identical electrons in the same space because a force exists between them to push them apart from each other. But you can if they're different. And one way that they found that electrons could be different from each other was in this kind of bipolar sort of way, that they're either this or that. There was a characteristic associated with the electron that was in a binary-like sense, a 0 or a 1. And they thought about what it could physically represent, and they thought, relating it back to the solar system, that it was a little bit like the axial rotation of the planets. Some planets rotate clockwise. Some planets, or well, perhaps moons, could rotate anti-clockwise, depending on how you observe it. Now, this means there's fundamentally a spin one way or the other for planets in the solar system and nothing in between. It's a two-state system. Now, though the electrons themselves do not physically rotate, they don't physically have a surface like a planet, and most of the time they don't even act like particles like a planet, we do give them this property of spin. And because we have spin up and spin down, or whichever way you want to look at it, it means that we get two electrons possible to exist in pretty much the same space. So they can occupy an orbital together. So what is the direct observational evidence for this? And it comes from the pioneers of spectroscopy, Kirchhoff and Bunsen. They burnt a lot of things, and they looked at the colour of the light that was given off. The spurs through a prism enabled them to see the rainbow or the spectrum of these things, and they found dark lines in those spectrums, lines that gave away movements of electrons in the atoms of the gases that were excited. So what did they observe? Well, they observed these lines. The most obvious were these really sharp lines that seem to be present in all elements. So they call these sharp lines S-lines. Then, with those elements that are first observed in those elements like carbon and nitrogen and oxygen, we had P lines. The first elements that displayed a third set of lines, the D lines for diffuse, were the transition metals. And then things at the very bottom of the periodic table even had some really fine fundamental lines, or F lines. So it was clear that as the element got heavier, it gained more and more ways in which it could move electrons around. We realized that this was their orbitals. So let's take a look at them one by one and see how this works. The s orbital, those lines that are present in the spectrum of hydrogen and helium, it's a spherical shell of electrons, and two electrons can possibly fit in there. Hydrogen just has one. Helium, a second electron goes into that same shell. On a diagram, we quite often draw them at either sides, like a ring with them at either sides, but that, of course, is localizing them in space, and we just don't know where they are. And so what we could draw is like a ball to represent the cloud where we could find it if we looked. Now, how we would write this down is with this notation. You can see hydrogen there, that electron has a configuration of 1s1, 1 being the principal quantum number, it's the first shell. It is an s orbital, the spherical orbital that produces those sharp lines, and it is number 1, the first electron into that orbital. You see helium, it's 1s2, and that is the orbital filled. Now, all elements beyond helium are going to have a full 1s orbital. It just means that further orbitals build around the outside. If we look at lithium, it has 1s1 and 1s2, and we shorten that hand to say 1s2, because if it has 1s1 and 1s2, then we can shorten it by just saying, yes, it is full. 1s2 is the full shell. What happens beyond that is it starts to gain a second s orbital. The 2s1 electron goes into another s orbital, but in the second shell, having a principal quantum number of 2. So starting in the spectra of boron and then present in all of the elements heavier than that are lines that we attribute to p orbitals. Now these aren't spheres, they're not round little shells. They are in fact dumbbell shaped, and you get one dumbbell along the x-axis, one along the y-axis, and one along the z-axis, each being able to contain 2 electrons. Now it's not the case that there's one electron in one side of the dumbbell and one electron in the other, but the electrons could be found anywhere within that whole shape, including both of them on one side. Now with these, the 1s shell is smaller, of smaller radius, and sits down within this. The 2s is bigger, but still sits smaller than this structure. These p orbitals extend much further out. They are the further out electrons. Now, because we can fit 6 in these and 2 in the 2s subshell, then what we're going to get is 8 in this shell altogether, and that leads to the electron configuration that we explored at GCSE. You can see how to write this down. Well, if we were talking about boron, it has 1 electron in one of these p orbitals. It would be 1s2 for the first 2, 2s2 for the second 2, and then 2p1, with the 1 being the first electron to occupy one of these p orbitals. You can see here that group 3 always has an np to the 1, group 4 have np to the 2, group 5 always have np to 3, so it's always the group minus 2, because 2 of those electrons have come from s orbitals instead. Now when we get to neon at the end of that row, so we're talking about group 8, we find that it has got a full shell. It means that there are electrons in all of the available places within its orbitals. There are 2 electrons in its 2s2 orbital, and there are 6 in the p orbital positions. Beyond those p orbitals and in the third shell, we have these things, d orbitals. 10 electrons can exist in a variety of different 4-leaf clover-shaped orbitals and 1 donut shape. These extend really quite far away from the nucleus and are responsible for the electron configurations of all of the transition metals. That's why they're called the D block metals sometimes. Now, a very curious thing has happened. The first time we see d orbital electrons is in the third electron shell. Now, you would imagine that means that we should draw the elements in the third row or the third period of the periodic table, but they don't appear till the fourth. And that is basically because the 3d orbital has an ever so slightly lower, or I should say higher energy than the s orbitals of the 4s shell. It means that electrons will fill into the 4s shell before they will fill into the 3d shell. That's complicated, isn't it? Look at this next example, it will make it more clear. Beyond the d orbitals, an element, if it is large enough, can have an f orbital. And this is basically the explanation for the electron configurations of the lanthanides and the actinides, those rare earth metals that sit normally at the very bottom of the periodic table. Given them their rightful place in between group 1 and group 2 and the transition metals, you can see that these form a variety of different shapes and can have a very large number, 14 electrons altogether. And this explains all of those. You can see the heaviest element yet discovered, oganesson, has the electron configuration. Are you ready for it? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 5f14, 6s2, 6p6, 6d10, 7s2, and then 7p6. Now, you will not be expected to remember all of that, but you will be expected to know all the way into the d orbital electron configuration. Now, you may have heard me refer to the word subshell there. I just want to be clear what I mean by that. Everything at n equals 1 is part of the n equals 1 shell. Everything at n equals 2 is part of the n equals 2 shell. But the orbitals, the p orbitals, together combine to form what we would call a subshell. So when I'm talking about the p orbitals at a particular shell, that is the subshell. So as you can see in that previous example of organism, I had like 3s2, 3p6, 3d10, and then we're talking about 3 subshells there. We're talking about the s subshell, the p subshell, and the d subshell. So yes, why does the 3D subshell fill after the 4S subshell? Well, look at this energy diagram here. What you can see is that the 4S subshell is ever so slightly lower in energy than the 3D subshell, which means that favorably electrons will fill into the 4S. There will be 2 that go in there before they fill into the 3D. You can see that further up it becomes really quite complicated. These become overlapping. And if you want to know a little bit more about this, this is the Aufbau principle. It basically is something you just need to remember when we're dealing with transition metals. It's all right saying that there are orbitals that can be filled by electrons, but how do those electrons fill those orbitals? Well, basically they fill them with respect to their spin. So in each one of those, for example, the 1s2, we get 2 electrons filling that particular orbital, one spinning with the arrow denoting it up, and the other one spinning with the arrow denoting it down. Now it's the same for the 2s2. For the 2p6, we get 2 in the x, 2 in the y, and 2 in the z. But how do they fill? Well, what you'd actually find is you'd get like an upward arrow in the x, an upward arrow in the y, an upward arrow in the z, and only when there is one electron in all 3 will then the second electron start to join. You would never get a pair within a given subshell fill when there are empty parts of the subshell. They'll be like up, 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 and then down, 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 like in that sort of sequence. So a nice example of that, nitrogen. Its 1s subshell has an up and a down. Its 2s subshell has an up and a down. 3 more electrons to fit in there, and what they fill is they take up their positions in the px, the py, and the pz, all pointing upwards. As we go to oxygen, the next element, how does the next electron fit? Well, it goes back into the px, but the other way. And so you can see that they fill up that way, with one spin direction filling them all, and then further electrons coming back in with the opposite spin direction. To save time, we don't have to list the entire electron configuration, 1s2, 2s2, 2p6, 3d10, all of that sort of stuff. We don't have to do that. What we could just say is that this atom has the same electron configuration as the last Nobel gas, with the addition of any more electrons it might have gained since then. So, for example, sodium. Sodium is group 1. The last noble gas was neon, 1 element before. This has gained 1 3s1 electron on top of what neon had. And so what we can do is we can say it was like neon and put that in square brackets, but with an extra 3s1 electron. Looking at the outermost electrons of any then element enables us to categorize the periodic table into 4 areas. You've got your S block, which forms group 1 and group 2. You've got your D block, or your transition metals. Your P block, which contains all of the non-metals and a few of the metals as well. And of course your F block, your lanthanides and actinides at the very bottom. So what happens when we form an ion? When we give enough energy to an electron for it to leave, normally the one electron that requires the minimal amount of energy to leave, the one that will leave first, is the electron that has already the highest energy, the one that is the furthest away from the nucleus. And that would be the very last electrons in the electron configuration. So in this particular example, these 4p6 electrons are the ones that would leave the minimal amount of inputted energy. To ionize this, to turn it into its very first ion, missing one electron, we just need to give one of these 4p6 electrons enough energy to escape the attractive forces of the nucleus.